Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Jewell, who is an associate professor at the University of Wisconsin, Eau Claire. Hi Matthew, thank you for speaking to us.
Hi there, and thanks for having me. Really glad to be able to do it.
Wonderful. Let's begin. Let's start with, how did you end up in your current research field? What's your story?
Yeah, so I started out as an undergraduate at the University of Wisconsin in Madison, and I got right away as a sophomore into a lab working on superconductors. I was just doing metallographic sample preparation and some basic SEM imaging of materials for them, and I ended up staying with that through my undergraduate time and really just started to enjoy more and more what I was doing as I kind of learned more about the field. So I took what, at least in the US, is a pretty unconventional path. I stayed at that institution, continued working in that same research group into graduate school with David Larbalestier, who's one of the real foremost superconducting materials researchers here in the US. And I would have stayed and probably finished out my PhD there at Madison, except that with about 2 years left on my timeline, our research group moved down to Tallahassee, Florida. And this was a big change for our group, but it was really a wonderful move because it allowed us to interact with the National High Magnetic Field Lab, which is down in Tallahassee. And they're very interested in using superconductors, that's my area of research, to build bigger and better magnets for their user base. So I ended up doing 2 years there in Tallahassee. And then while in Tallahassee, got connected with this ITER project, which is a nuclear fusion reactor being built in the south of France. And this is a big international project. And at the time, they were having some challenges with their superconducting magnet conductors. And so our group got involved, and I ended up doing a PhD thesis centered around how the superconducting materials for their system were made and what some of their unique strengths and challenges and vulnerabilities were. So then after my PhD, then I ended up going to ITER, going to France and working there for 2.5 or 3 years on a postdoc in the magnet division and working on the magnet systems for that fusion device. And then found my faculty position that I currently have back here in Wisconsin. And so we came back to the US then and have been here since.
Okay, wonderful. That sounds like a very, very interesting path. And you've had some experience abroad as well. I'm sure that must have been really exciting and you learned a lot. Wonderful. So could you tell us where does this super interesting research, where does it fall in this big picture of materials and nanoscience? Where does it fit in the puzzle?
Right. So when we talk about superconducting materials, there's a lot of different length scales, let's say, at which we are trying to answer different questions. So some people in materials research for superconductors are focused on really the macro scale. How do I put wires together into some kind of cable or conductor? How do I integrate that into a magnet system? How do I insulate it? How do I protect it against these disruptions we call quenches? Other people are focused more at the micro or the nano scale. How do I do the heat treatments and other processes that I'm going to need to actually form the superconducting phase in the material? How do I optimize the grain structure and even the nanostructure to make the material perform as well as it can? And here it's probably worth diving in just for a minute or two into one kind of detail that's important. So in a superconductor is kind of an interesting quantum state of matter. And in a superconductor, magnetic field lines are quantized. So within the superconductor, most superconductors, so-called type 2 superconductors, magnetic field lines can penetrate the superconductor, but they're in these individual quanta that we call fluxons. And these flux lines, if they are allowed to move within the superconductor under the Lorentz forces that are sort of naturally present, the magnetic field and the current conditions lead to these mechanical forces on the flux lines. If they move around, they're going to generate heat. So that's very problematic for a superconductor. So as materials engineers, you have to pin those flux lines. We have to fix them somehow in the material so they can't move around. And we do that through defect engineering. Like a lot of other areas of material science, we intentionally build in defects to the material to kind of grab and pin these flux lines so that they will be stable when we actually try and operate the material in real life. And so we can do that through defects like grain boundaries, through precipitates, through other defects that we intentionally engineer into the structure. And so as you can imagine, that defect engineering can happen down really to the nanoscale because these flux lines exist on the nanoscale. So all the way down at length scales of 5 or 10 or 20 or 50 nanometers, we are trying to optimize the structure there. But then we also need a microstructure that is going to allow current to flow through some kind of, whether it's a filamentary structure or a tape type material. We have to optimize that level. And then, as I've already mentioned, we of course have to optimize the wire or the material at the macro level. So there's really a variety of length scales there. And that's pretty traditional material science if you think about it, right? As materials engineers, we're always used to thinking about how is the material behaving across different length scales. And this is, and for me, superconducting materials are just a nice example of that, of having to be thinking about all these things simultaneously and how they fit together to get the ultimate performance that you want.
Okay. All right. Yeah, that sounds super interesting. Wow, that's wonderful. So it sounds to me that you have done in the past a lot of interesting experiments, and you're also doing a lot of interesting projects at the moment. So if you had to pick one project that you worked on or an experiment that you worked on, your favorite or the one you're most proud of, could you pick one? I know it's a difficult question to pick one. Probably you have several favorite. Just take one and explain it to us in really simple words in the section we call In Other Words.
Yes, so indeed, as you say, of course, I love all my children equally, but probably the project I worked on that would have the most resonance, maybe for people outside superconducting materials, was my time in France when I was working at this project called ITER. So ITER is a very ambitious nuclear fusion project. It's trying to make fusion energy commercially viable by demonstrating for the first time in human history that you can sustain a nuclear fusion reaction on the order of minutes, and that reaction can be net energy positive, that we can get out more energy from the reaction than we put in, including all the energy inputs, the heating of the plasma, the cooling of the magnet system, all the things that cost energy to get the fusion reaction to go. And ITER is a particular style of nuclear fusion called magnetic confinement. It means that in order to make this plasma hot enough and energetic enough to cause the fusion reaction to occur, you have to superheat it to a point where you really can't hold it in a bottle. There's no crucible you're going to put this plasma into without kind of burning your crucible. So instead, it's magnetically confined. The plasma is literally levitated in this donut-shaped device called a tokamak, and it's levitated and sort of stirred inside here, but it requires a very complicated magnet system, as you can imagine, to keep it in the shape and density that you need to allow the plasma to occur. So it's very sophisticated. First of all, very sophisticated design for such a device, but then also very challenging to actually build these magnets and get them to do what we want. So in this ITER project, there are 3 primary superconducting magnet systems, and I'll name them briefly. The names aren't so critical for everyone, but there's the toroidal field magnet system that actually goes around the donut. There's the central solenoid, which sits in the middle and helps to drive and stir the plasma. And then there are these so-called poloidal field coils, which help to shape the plasma and keep it stable. So each of those magnet systems uses superconductors to produce the very, very large magnetic fields that are needed for the device without enormous energy budget that would then no longer make the device net energy positive, since that's a main goal of the project. So I helped work on those conductors, helping to design them, helping to design quality tests. I think one of the things that our team was most proud of there, this was the first time ever that some of these superconductors, in particular one called niobium-3 tin, first time that a niobium-3 tin superconductor had ever been produced on the quantity of hundreds of tons. So we involved 8 manufacturers around the world in this procurement. We had to get them all up to speed on the same kind of quality standards. They all had to ramp up their production, and we ended up producing 500 tons of nibin-3 tin over a period of something like 5 years. And this was really a major accomplishment for superconductivity, for superconducting materials. Built out a lot of industrial capacity around the world that can now be used by other projects. So I think that was one aspect of the project that we're really proud of.
Okay. Wow, that sounds like it's a symphony. So many things have to work together in such synchronized way. That's wonderful. Out of curiosity, what were the sizes, what were the dimensions of these magnets or these donut-shaped magnets that you mentioned?
That's a great question. So the eater device itself is going to stand, the entire structure is going to stand something like 60 meters tall. So it's an enormous structure. When you think about the actual kind of size of the magnets, they're something like 10 meters tall. So that's 30 feet here in the US. So each of these magnets is several stories tall, weighs something like 300 tons with the case around it. And so there's several, with the 18 toroidal field magnets, you already have several thousand tons of magnet conductor plus structural material. So really a massive project. In fact, here's just one interesting tidbit. The location of this reactor in France is inland, about an hour from the ocean. So there's a big question of how are we going to get some of these very, very large components, which are manufactured offsite and have to be delivered. How are we going to get them actually to the site of the reactor? And in the early days, there were some kind of crazy ideas floated, like maybe we use a blimp or something like that to sort of float them in. But in the end, these ideas were discarded, and the French had to sort of plan and build an itinerary, a route where bridges were reinforced, power lines were taken down or buried, and they built sort of a what in the U.S. we would call a crawler, sort of a device like our NASA uses to move space shuttles out to the platform for launch. This kind of large crawler device with many wheels, and it goes very slowly, maybe 10 kilometers an hour, and someone with a little remote control walks next to it, and it takes 2 or 3 days from the port at Marseille to get inland to the reactor at ITER, and they bring these multi-100-ton magnet components up the route that way.
Wow, that I can understand now why you picked that as your favorite, or let's say not favorite. I mean, that's a very strong word, but one of the most interesting projects that you were involved with. That's wonderful, awesome. I hope you can talk about that as well when you're curating the Twitter account. Some pictures maybe to give like a small person standing next to this big piece of 60 stories tall or something like that. Okay, wonderful. Matthew, let's go a little bit into the other side of a academic researcher, so to say, the teaching. Do you teach, and if you do, which courses would you like to mention?
Yeah, I teach a great deal, and in fact, this is something I'll also highlight on the Twitter account a little bit when I have it. Here at Wisconsin-Eau Claire, we are actually primarily a teaching university. We are a so-called primarily undergraduate university. We have no graduate program in material science. All the research I do is with undergraduates, and that's quite unusual. I think in the US, we may be the only one or possibly one of 2 universities in the country that has a material science engineering program that works exclusively with undergraduates. So that that produces some real opportunities, and also from a research side, you can imagine some challenges, right? So we have to find projects that are a good fit and that work well for undergraduates, but also do things that are relevant for the field. But you asked about teaching. So yes, I do teach then typically something like 3 classes a semester, 1 or 2 lectures, and then typically a lab. A couple of classes that I'm teaching now and really enjoy. I teach a phase transformations class, which is sort of a physical metallurgy course. So the basics of phase, nucleation, and growth, the kinetics of phase transformations, those sort of topics. I think that's a really important foundational course for students, and I think really helps them to appreciate the breadth of things that you can do in material science, and also helps them appreciate how some basic engineering principles allow us to do a lot of design work, a lot of materials design, to get the things we want out of materials. So I enjoy teaching that course. And then also right now I teach our senior capstone course. So like in many engineering disciplines in the US, senior students in their last year have to do some kind of independent so-called capstone project where they work on a year-long research or engineering design project, and they try and solve some kind of a question or a problem for an external client or a company they work with or someone on campus here. And that's a really fun class to teach because students have to use a lot of creativity, have to think about kind of design maybe in new ways that they haven't thought about before, and really helps to give them a good professional basis then for going out either to graduate school or to get a job in a materials related industry.
Okay, that sounds like a very, very well thought through program, which is a combination of everything, and you try to equip the undergrads with as much practical and creative thinking as possible.
Right. One reason I've always enjoyed being part of material science, I think one reason I probably picked it as an undergraduate major is material science is growing a lot right now in the U.S. In the universities, but it's always been much smaller than, for example, mechanical engineering programs or electrical engineering programs. And I really enjoy that. I really enjoyed as a student having that more personal connection with my faculty members and being able to learn from some real, luminaries, but in kind of a smaller setting. And I really enjoy them the chance to do the same now for my students and having these upper level classes that are small and we can know everyone and work with them on a one-on-one basis. And yeah, that's a nice way to be able to do university engineering education, I think.
Yeah, absolutely. I agree with you completely. You're trying to enrich their early research experience as well. Speaking of which, I hope your research experience so far has been wonderful and it will continue to be amazing in the future as well. However, if you had 3 wishes to improve it, what would you ask for? And I'm not promising anything here.
Right. Yeah. So I think in our sort of unique context as a undergraduate campus that's trying to do a lot of still helpful and good research work, I think one thing would be better or easier access to certain research facilities at larger institutions. So we have a lot of good facilities here for doing materials work, but also sometimes we need specialized equipment that only exists at a larger university. And sometimes there can be bureaucratic barriers, let's say, to making that happen. So there are times when I could wish for just easier facilitation of some of those collaborations. Also, I think it would be nice to see more federal research funding agencies in the U.S. follow the example and the model of the NSF, the National Science Foundation, in dedicating some portion of their research funding to primarily undergraduate institutions. So when NSF reviews research proposals, in certain disciplines at least, they have particular pieces of their research budget that are held for undergraduate institutions, and then the competition is just amongst those undergraduate institutions. And that really helps to create a really healthy research climate at some of these schools. In particular, chemistry does a good job with this at NSF of kind of reviewing grants against other chemistry institutions at similar sized schools. And I think more federal agencies could follow that lead, and that'd be a really healthy and constructive thing, I think, for research in the U.S. And then you asked for 3, so I don't know. The other one, I think I would just say the same thing that all of us would say, just more hours in the day, right? There's never enough time to answer all the emails and do all the projects and prepare everything the way I would like to for classes. So right. if you could wave the magic wand and just give us a few more hours every day, that'd be great.
Okay, now that we're talking about the hours, how many hours would be enough? Tell me, how many hours would you ask for?
Well, I don't know. I think that's. I'm sure we would just fill it with too many things as well. So hard to say.
Yeah. Okay. All right. That's what I thought. I wish I could grant those wishes. I hope for the funding and for the reducing the bureaucracy part. I hope we are moving towards the right direction. Hopefully, sir, the federal funding agency are listening to this podcast and they will take a note. We'll keep our fingers crossed for that. All right. Let's go a bit into the fun part. So, what are you most looking forward to in the next 3 months, other than Christmas and New Year's, of course?
So this year I have a new project which is just starting up, and I'm very excited about it. I have a small grant through the state of Wisconsin to help manufacturers in Wisconsin, those in the materials industries and manufacturing industries, to better align themselves for so-called advanced energy production fields. So this came out of my interest in fusion and realization that now, in addition to big government projects like ITER, we're also seeing in fusion several smaller privately funded efforts, including being funded by some pretty large and well-known venture capital firms. There are projects in the U.S. and in the U.K. That are trying to produce fusion on a somewhat smaller scale and a more faster commercialization path. And that just got me thinking, realizing that here in this part of the country, in the Midwest of the U.S., we have a lot of manufacturing capacity that, let's say, is structured or geared towards very traditional areas of manufacturing, like automotive components and tooling and kind of typical machining type areas. But really, future growth in some of these areas are going to be in things like wind energy and solar energy and potentially even nuclear fusion. So I'm trying to put together a survey of what are capabilities here in Wisconsin for manufacturers, and how can some of those manufacturers better align their capabilities with future manufacturing needs rather than maybe current or past manufacturing needs. And this is being funded by a group out of Madison, Wisconsin, called the Tommy Thompson Center. Tommy Thompson was a former governor in Wisconsin, and the state legislature has kind of endowed this agency or group to fund some of these initiatives that are kind of forward-looking and helping Wisconsin to realign in certain ways. So that's something I'm looking forward to working on here in the next few months, and I think will be interesting and kind of for me a new challenge too.
Okay, well, we wish you a lot of success and a lot of exciting experiments within this project, and I hope everything works smoothly in a synchronized way, as you will be working with a bunch of different stakeholders, so to say. Good luck for that. Before we let you go, could you address or tell us about the big challenges or these big questions that the materials and nano community is working towards solving?
Yeah, I think, I mean, of course, there are a lot of very interesting areas of materials research and nanomaterials research happening. I think what I'd like to highlight, though, is I think there's a danger as we are becoming more and more specialized. And this is maybe not new, but there is really a danger, I think, that the materials community is fracturing a little bit just because of kind of over specialization, that there is not as many kind of common threads holding together these very disparate research programs in biological materials, energy materials, materials for computational things like quantum computing, and each of these is really kind of unique, and so the field is becoming kind of further and further I think specialized that way, and there's obvious reasons for that, and probably no turning that around exactly, but I think we should be more thoughtful as a materials community about what that means and how we still kind of work together. And similarly, then, how do we sort of integrate all these interdisciplinary approaches? As an educator, we want to train our students to a level where they have some real skills in certain areas, but we also want them to have some breadth. We want them to understand how different segments of the materials community fit together, and that gets more and more challenging as various fields within materials get more and more specialized. So I think that's something that we really need to think through carefully as these very interesting areas move forward. How do we still teach and train students to be able to operate effectively in all of them?
So keep kind of the interdisciplinary aspect of the material science intact while specializing in certain niche fields, so to say.
Yeah, just balancing those needs. That's right.
Okay, all right. Yeah, that's a fair point. I had never thought about that. That's correct. I agree with you on that. All right, Matthew, thank you very much for speaking with us. It was lovely to speak with you and understand a bit of what your research has been and what your current research is. We hope you have fun on the Twitter channel, and see you there.
Thank you. Appreciate it. And I really look forward to being able to put some of this out there via Twitter.
Wonderful. Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.